Welcome to a lesson with Dr. Pal. In the last video, we discussed powers of x plus 1 raised to a power. Now, let's take a look at x plus y raised to a power. Is there much difference? Let's think for a minute. If we were to multiply this out, which is x plus y cubed, let's just do it piece by piece. Let's just look at the first two for a minute. If we look at the first two, we could almost think of x plus y distributed as a chunk, distributing into the x and then into the y. So x plus y, y. And that would be the first bit. Okay, then we would distribute that in. X squared plus yx plus xy plus y squared. X plus y. Then we could take this x plus y and distribute it to each of these individually. And doing so, we'd have x squared, x plus y, plus, let's write that as xy, x plus y. In fact, notice you have an x, notice this is an xy and an xy, so we could have combined terms. That could be a 2xy. So really, this is just a 2xy right here. It's 2xy, x plus y, plus, and then we have a y squared times x plus y. Then notice this can distribute in, x cubed. This is not the way that we're going to be doing it, but I'm doing this for sake of illustration for a minute so that we don't have to do it from here on out. 2xy squared plus, let's make that xy squared plus y cubed. Notice that every single term that we have from this distributing comes from one thing in here, and from this first term, times one thing from the second term, times one thing for the third term. In fact, we get very precisely. We could actually just do this by doing that. We could say, okay, how many different ways are there of choosing something from this term? All right, we could choose an x or y. So we could like go first term, second term, third term. And then we could say from the first term, let's do x. So do x, second term, let's do x, third term, let's do x. Then we could say x, y. We could have chosen these from there and that from there. This is a different way of doing it. Or we could have done x, y, x, y, y. Or we could have done all the same things again. 3, 4, with doing x, y, or y, x, y. Notice that these are all the different possibilities. Now notice, if we multiply this out, we get y cubed. This right here is y squared times x. That's that guy right there. Then we have y, x, y. So that's like xy squared. So there's an xy squared here. And also look, there's another xy squared here. So these two together, you add those two, if you multiply them and then add them, you end up getting that guy. Similarly, if you do, let's see, this is x squared y and x squared y. If you did these two guys right here and multiply them and added them, you would have, so these right here would take you to this guy right there. Then what about this one, xy? That would have taken you all the way over to here. And you see this one right here? So it would have taken you there. In other words, we could have multiplied this out, or we could have just made a list and looked at all the different possibilities. What lessons do we learn from this? We're just going to take some observations, and we're going to use those observations. Observation. Every single term has exactly 3 things in it, an x, y, or whatever. So it kind of has like a total, if you were to add the exponent of x and the exponent of y, you always end up getting 3. Hey, and that's handy because we were raising x plus y to the third power. We always end up getting an exponent of 3 down. Okay. Hey, maybe that is useful because if a term has an x squared in it, then we know it must have a y. If it has an x in it, then we know it has to have a y squared. If it doesn't have any x's, then it has to be y cubed, and so forth. So, like, if we're thinking about powers of x, like with place values, like we were doing with that, we were doing 1, 1 times 1, 1. These place values depended only on the power of x. So, when we multiply these out, we ended up getting this, and in the multiplication. And this right here, so this was the power of x squared. This was the power of x, but hey, if this was squaring, then we know we'd have to have an xy, and power of 0, we'd have to have a y squared. In other words, this algorithm works perfectly well and tells us, and the place values actually tell us which term we're dealing with, just perfectly. So we can use the exact same algorithm and Pascal's triangle even to determine x plus y to a power. So to do this, we do this again, multiply. Let's see, that's a multiplication symbol. So we get 1, 1, 1, 1, add 1, 2, 1. Oh, what does that mean? This means means 1 times x squared, but it's still an x squared. This is a 2x, but whenever we have an x, we also have a y. Whenever we have x to 0, well, we must have 2 y's, so a y squared. And so this would be the result. X squared plus 2xy plus y squared. Hey, the coefficients are the same. And here we go down with powers of x just like we would before, but then we just have y fillers. That's about it. So let's try the next one. What if we did, x plus y cubed? Let's see. We multiply by, let's think of this as being xy, and this as being this guy right here, thinking of our powers in the way we were. And we end up getting 1, 2, 1, 1, 2, 1, and 1, 3, 3, 1. Okay, that means that x plus y cubed is simply x cubed plus 3x squared, but then we put a y, plus 3x, then we put a y squared, plus y cubed. That's it. So Pascal's triangle is a nice way of doing x plus y to a power. Here, Pascal's triangle here. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And so in this case, let's see what x plus y raised to the 5th power would be. Be x to the 5th plus 5x to the 4th, put a y, plus 10x cubed, put a y squared, plus 10x squared, put a y cubed, plus 5x, put a y to the 4th, plus y to the 5th. Notice these exponents always add up to 5 when we add them together. Thanks for watching.